Got a class. Oh, wait. Everything's just online now. I'm a teacher.
Never say I can't do a smooth transition. Hello everyone, welcome to Recitation. Hopefully you guys enjoyed my little 50-50 game in the announcement this morning. Had some fun making that. Some good music today. Never listened to the MapleStory soundtrack before. I see there's a bunch of questions already being asked in the Q&A about review-related stuff. Practice exam, I don't know how long that will stay open, but the file will at least be there forever for the rest of the semester, so you can use that if nothing else. I'll talk about what this recitation is going to go over in a second, and we'll have some time for a review at the end. With that said, I should have some wonderful TAs helping me out in the Q&A, so hopefully those things will go smoothly. But otherwise, I will go ahead and get started. So, for this week's recitation, your important announcements. You have a homework that's due not immediately soon, but still in the near future. You've got AVL homework that's due this coming Monday on the 19th, so still 6 more days on that, but it is more difficult homework, so I would recommend working on that one if you haven't already. Homework 8 is the sorting homework that's going to release this Friday. It's not due for 2 weeks. As I mentioned last time, I recommend starting on that one a little early, not because it's difficult, just because it's long. We'll be starting to cover some of that material today, but we'll get to more of it next week and the week after. That's the first algorithm homework in this class, and in general, it's a little bit easier than stuff like homework 7 and homework 6. Exam 2 is tomorrow. I really hope that's not news to anyone. You've got that window from 6 a.m. to 11:59 to take it. I recommend that, or I don't recommend, but if you don't start before like 10:45, you're going to get cut off when the exam finishes. So please start before then. Hope if you have any issues whatsoever with stuff, you should email your professor and CC the head TAs. That would be me and Landon. Otherwise, most of the stuff's going to work exactly the same as Exam 1. If you didn't notice in the topic list announcement, we mentioned it there. We're explicitly stating it's going to be all of like the multiple choice questions, so big O scenario stuff first, then diagramming questions, so like remember that like BST diagramming from Exam 1, etc. Then all the coding questions. So if you want to start with the coding questions, go to the end of the exam first. You should be able to jump around to whatever question you want. The practice exam answers should be on Canvas under the practice exam folder. Worksheet for this week should also be on Canvas at this point. There's going to be a review link I'll give out later, just like we did for Exam 1. It's that Kahoot that there's no real way for us to do. If you want to look at the link, it's probably pretty easy for you to guess what it is, but I'll put it on screen later. The stuff we're going to do today is we're going to cover 2 for trees. We're going to do a brief introduction into sorting, and then we've got exam review. With that said, give me one quick second. See, someone asked, how do I explain to my roommates that my recitation is funny? They see my antics. They've sounding boarded some of them, and one of them's taken this class before. Alright, let's go ahead and start talking about 2 for trees. That's probably one of the biggest reasons a lot of people are going to be here today, because 2 for trees can be scary, and people definitely want to get a chance to look over them. Let's see. The analytics are bad, but I might be able to estimate how many people are here. Already over 100 here. Not too bad. So, 2 for trees. These are very special trees. We've talked about a lot of different kinds of binary trees in this class so far, but we haven't talked about any trees that aren't binary. You'll also notice, if you remember from the properties we talked about really early on for shape, we never talked about a tree that's full. So here we're going to kind of kill 2 birds with 1 stone. These are going to be trees where every node can have multiple data and can have multiple children. So the multiple children part should kind of be obvious, but I'm going to like specify this is like not just 2. But the multiple data part, that's the big thing that we have with 2-4 trees. That's different from what we had with binary search trees, heaps, and AVLs. The big thing with 2-4 trees is, as the name might suggest, they can have between 1 and 3 data in each node. I know that's very intuitive. We'll get to the 2 to 4 later. But something I'm specifying here is I'm saying it's between 1 and 3 data in a stable state. It's possible that in the middle of our operation, we might have 0 data or we might have 4 data. But before we start the operation and after we finish, every node should have between 1 and 3. It's just like saying an AVL is always balanced in its stable state. It's possible immediately after we start doing an add, we get to an unbalanced AVL, but then we do the rotation to fix it. Very similar thing with 2-4 trees. We're going to do these operations to fix the tree if we ever get 0 data or 4 data. Another nice detail about, so the 2-4 tree, the number of children, this is the big part. If a node is not a leaf node, meaning if the node has any children at all, it will have exactly the number of data in the node plus 1 children. So if it has 1 data, it has 2 children. If it has 2 data, it has 3 children. And if it has 3 data, it has 4 children. So this is where the 2 to 4 comes from, because nodes have between 2 and 4 children. And again, this is in steady state. As I mentioned, it's possible for nodes to have between either 0 or 4 data in the middle of an operation. You'll see that later. But a nice thing is, even when that happens, this rule still holds. So when a node has 0 data, it will have 1 child, and when a node has 4 data, it'll have 5 children. Order property. All of the data in any given node is in ascending order. I can add that stipulation here. And you can look at the relation between like the children and the data in the node. So if we have a node with 3 data, like W, X, Y, the data here that's kind of to the left of W is all less than it. The data here that's like in between W and X follows in between W and X. Here, in between X and Y follows in between X and Y, and over here is everything that's greater than Y. So those should mostly be intuitive. Another thing, and again, this holds for subtrees as well. So this is like this node and any subtree beneath it, etc., etc., when you have large 2-4 trees. And our final big property for 2-4 trees is that all of the leaves in a 2-4 tree have the exact same depth. So we don't have, it's impossible for us to have an unbalanced 2-4 tree. We always have a nice even, everything ends at the same depth, which means that the height of the tree is always going to be O of log n. Now, a nice consequence of this is this property is going to make us so that our tree is always full, because our tree always has a 0 if it's a leaf, or the maximum number of children, as opposed to this. Oh, I did say these are the same thing. So this and this, these are the same. I wrote stable and steady, different places. That's my bad. So, all leaves have the same depth. So this means that our tree is going to be full, and this property saying that all leaves have the same depth means that our tree is also going to be complete and balanced, because we're never going to have like weird broken up levels, because everything's going to go nice and smoothly from the root all the way down to the bottommost level. Efficiencies, I mostly just put here because of lack of space to put them on later pages, but because we have this balanced, full, complete property, and height is always log n with no degenerate case, all of our efficiencies for stuff for add, remove, and search are going to be log n. The height being log n is a consequence of all leaves having the same depth. Because all the leaves have the same depth, we can just traverse down to one of them, count the number of layers we go past, and that's our height. So we don't need to traverse everything in the tree. A lot of questions in chat. TAs are getting to those. Thank you so much. I'll give a couple more seconds for this, and then we're going to talk about adding. We'll have examples for adding and removing for all the weird cases. Don't worry. Okay, if you guys could hold off on some of your review questions for now, so like asking me to cover stuff towards the end, hold off on that for a little bit. Right now, it's just kind of making the Q&A really cluttered for questions that people are asking about the current topics. I'll give you time later to ask your questions then, So just hold off on them for now. If you need to like write them down somewhere just so you don't forget, that's fine. Obviously that's fine. I can't really stop you. If I could stop you, that would be a little scary. But just hold off on those questions for now. We will get to them later. We should almost definitely have time at the end of this recitation. But that is an excuse for me to get onto the next page, and let's talk about adding. Adding into for trees overall isn't that complicated. Most people don't have that much issue with adding. Removing tends to be the big issue. So, just like we did with like BSTs and AVLs, we're going to search for the correct spot to add at a leaf node. And applying all those order properties I talked about on the last page, like knowing which node to go to, like which two pieces of data our data falls between, we can use all of that information to traverse to some leaf node to add. Then we're just going to plop our data in the leaf node in whatever correct spot it is. So maybe it goes on the end, maybe it goes in the middle, whatever keeps our nodes sorted in themselves. If this operation causes some node to have 4 data, so that's an invalid amount because it's more than 3, we refer to this as overflow, then we're either going to pick the second or third item. Which we pick is implementation dependent. It doesn't really matter. Which we pick is really implementation dependent. It's not that big of a deal. It's kind of like predecessor versus successor. They'll both work. You just want to pick one to be consistent and like one for test questions. And we're going to promote that data, which means we take it and we push it upwards to the parent. If we happen to be at the root node, what we're going to do instead is we're going to push that data and create a new root instead of pushing it to its parent because one doesn't exist. Then we're going to split the node we promoted out of into data that's less than the promoted data and data that's greater than the promoted data. So it's going to create 2 new nodes. Then, if this promotion caused overflow, because when we pushed our item up to the node above it, that node already had 3 data, if we cause overflow like that, we're just going to repeat this entire process. So that's a lot of words. Let's see what it looks like in action. I'm going to take this 2-4 tree, and I'm going to try to add 44 to it. So when I add 44, the first thing I do is I'm going to try to find the leaf node where it belongs. So I look at this node right here. I say 44 is greater than all 3 of these pieces of data, which means I look at my rightmost child. This is a leaf node, so this is the node that I'm going to actually add 44 to. And if we look at the data, we can see that 44 goes in it's going to go in this leftmost spot to the left of 55. So our first intermediate step is going to look something like this. And if you want to simplify things for yourself, you're not going to need to write down like some of these things to the left that aren't changing, but I'll at least have them written so you can see what the full tree looks like. Alright, so this is the result of our add operation. We found the leaf it belongs in and we've pushed the new data in. Now we check whether or not we've caused overflow. We look at the node we've added to, we say, does it have 4 data? In this case, yes, this has 4 pieces of data. So now what I'm going to do is I'm going to say I'm just going to use the second element. And I'm going to promote the second element. So what that looks like is now this node up here, the node above it, that gets the promoted element. It just goes to the node right above it. These things over here didn't change. But this node is going to have split in half. So if I draw like the intermediate, the split is now just a node with 44, and then a node with 66 and 235. So the data less than the thing we promoted and the data greater than the thing we promoted. And if we look, it's really easy to see exactly how those are going to be assigned as children. And now we have this weird case, but remember I mentioned, even in these unstable states, we have 4 pieces of data in this node, we still have 5 children, which is number of data plus 1. And you'll notice all the order still holds. So this child's between these data are greater than this data. The next thing we do is, after we promote, we check if our promotion caused overflow. In this case, it did. So we're going to promote again. I'm going to use the same piece of data to promote because I want to be consistent across my implementation. I'm going to move to the left here. So here I don't have a node to promote up to, so that's just going to create a new root, which means that this big previous root node is going to get split with a 10 over here and then a 30, 55 over here. Then all these children are going to kind of follow along exactly where you would expect them to. It's pretty easy to see just looking at the order property that for all of these children, there's only one possible place on this bottom level that they fit. If you tried to put them anywhere else, you'd see it would be a violation of your order property. And if you miss any children, you'll see it's a violation of the shape property. So when you do two for tree operations, you should always check if your answer you got at the end is a valid 2 for tree. 1 data, 2 children, 1 data, 2 children, 2 data, 3 children. The order property holds for everything, and all of my leaves are on the bottom level. So this is my final answer. It's actually usually very difficult to get a valid 2 for tree with like whatever data you were supposed to add or remove and be the wrong answer. Very often, if you try to do the operation and you end up with a valid 2 for tree, it's usually the right answer. So always make that check at the end of your operations. That's more important, honestly, as important as knowing how to do the operation in the first place, is making sure to check at the end. I'll give a couple more seconds for people to write that down, and then we'll move on to remove. Remove is going to be the much harder thing. Couple more seconds. I'm gonna realize I should grab a couple pieces of paper for the review at the end, because that will be important to be prepared. Alright, then we'll move on to removing. Alright. There is a useful flowchart we've made for removal. You can find that link right here. That's tinyurl.com/2-for tree removal, so 2 for tree removal. That has a very useful flowchart that Neha has made that will help you. I think there's another flowchart or the exact same flowchart on Canvas under the Recitation folder. That's in like the campus/online Canvas. So go ahead and look at those. Those will be very helpful. I'm just going to try to explain the process kind of without a flowchart, because while flowcharts are very useful, they can seem scary when you see like all these possible options. But in actuality, 2 for tree removing at its core is a pretty simple process. And I'm going to hopefully try to explain that very well. But we'll see. 2 for trees can take a couple explanations to really get. So the first thing we do is, unsurprisingly, we're going to remove the data from whatever node it happened to be in. We can search it out using like our known order property and remove it. If the data we tried to remove is not a leaf node, we're going to use the predecessor or successor rule, so exact same thing as we had for BSTs, either the largest thing smaller than our data or the smallest thing larger than our data. Those are always going to be leaves, and we're going to turn this whatever removal we're trying to do, we're going to turn it into a leaf removal. We always want to do leaf removals. We never want to try to remove something from an internal node. We always want to remove the leaves. That's always the first step, is make sure you're removing from a leaf. The second step is you're going to check for underflow. What underflow means is if you've created an empty node. So this would be something with 0 data. Overflow was something with 4 data, underflow is going to be something with 0 data. Obviously that's an invalid node. We don't want nodes to have no data in them. The first thing we look at is we look to say if our immediate sibling has greater than 1 data, so if our immediate sibling has more than 1 piece of data in it, we're going to do an operation called transfer. Transfer is an operation that's very similar to an Avl rotation. It's pretty much the same thing. That's very important. That analogy holds true for a lot of things. transfer is pretty much an AVL rotation. Then we're done. If we do this AVL rotation in our 2-4 tree, we're done. There is no chance to have a underflow still existing after we've done this transfer operation. If this isn't possible, so if this if statement is false, if we don't have an immediate sibling with more than one data, we're going to do fusion. How fusion works is we pull data from our parent and fuse with the sibling. So as a note, we're not actually checking if our parent has more than one data in it. We're always going to pull from the parent if we're not able to do transfer. Which sibling we fuse with and which piece of data we pull down is going to be implementation dependent, just like which piece of data we promoted, just like whether you do predecessor or successor. It's not that important in the long run. The important thing for fusion is after your fusion is complete, you want to check if underflow still exists. It's possible that if your parent only had one piece of data in it, when you used fusion, you created more underflow in the parent. If that's true, you're going to go back up to this step. And why I say this step in particular is we want to check for transfer again. Your first step when handling underflow, always, 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 is check for transfer. Am I allowed to do transfer? If so, do it. If not, do fusion. Those are the rules of 2-4 trees, 2-4 tree removals. I'll say it again. If you have underflow, check for transfer. If you can't do transfer, do fusion, then check for underflow again. That's it. Always try to do transfer before considering fusion. I'll give a couple more seconds for people to write this down, then we're going to do 3 total examples. We'll do one example that's just a transfer, one example that's just a fusion, and one example that includes both fusion and transfer. Alright, let's go ahead and move on to our examples. So I'll give you a second if you want to write down what these two are before we start. They're the same tree, we'll just be doing different removals from each of them. We're not going to do the removals in turn, so that's why I've drawn the tree twice. But for our first transfer example, we're going to be taking this 2-4 tree and removing 17. So the first thing that's going to give us is we just remove 17 exactly from where it is. So now we have this. And you'll notice I have created underflow. Right here, there is a node with 0 data in it. That is underflow. Step 1, try transfer. So I look at my immediate siblings. People have asked, what is an immediate sibling? So, immediate sibling means for this node, my immediate siblings are right here and right here. These are my only 2 immediate siblings. 2 is not an immediate sibling of this underflowed node. That is an important detail. And also, we'll see an example later. Yeah, we'll see an example later that's also going to show another example of something that's not an immediate sibling. But just make sure it should have the same parent and it should be right next to the node. That's what immediate sibling means. In this case, to the left, I do not have more than one data, but to the right, I do. So this means I'm allowed to do transfer. So transfer is going to work just like an AVL rotation. I'm going to move one piece of data down and one piece of data up, just like we did with an AVL rotation. And what that's going to get me is this piece of data goes up, and this piece of data comes down. Now, because I did transfer, I know for a fact I have to be done with my remove operation. It's not possible for me to still have random incorrect things with my tree after I've done transfer, so I know I'm done. An important detail, though, for diagramming questions is you should probably check if your 2-4 tree is valid, because that's a good indication for whether or not you've done the question right. So in this case, 2 is less than 5, 10 is between 5 and 15, 20 is between 15 and 25, and 30 is greater than 25. Got 3 data and 4 children. So all that checks out. Now, an important detail, I said when we do this rotation, this transfer operation, that's very similar to an AVL rotation. Remember that in an AVL rotation, we have times where like random children of the nodes we're moving, those shift around. That is an important detail. Hold that in your mind, and later we'll do an example where that becomes important. But I try to use that AVL analogy for a good reason, because those children moving around is going to show up again. But we'll do an example of that later. For now, we're going to do an example of fusion. So remove 10. First step is we draw what our tree looks like just with 10 removed. Here, we have underflow. Step 1, check for transfer. I look at my 2 immediate siblings. This one has 1 data, so I can't transfer from it. This one has 1 data, I can't transfer from it. So I'm not allowed to do transfer. The only thing I can do is I can do fusion. Now, when I do fusion, I have to pick which of my 2 immediate siblings I want to fuse with. This is one of those implementation detail things that we would specify, so it's not that big of a deal. In this case, I'm going to choose to fuse with my left sibling. In that case, what I do is I look at the 2 pieces of data that are right above me, so this 5 and 15. Because I'm fusing with my left sibling, I'm going to pull the 5 down, the one on the left, and then these 2 nodes are going to fuse together. So what that means is I get this 5 in here, and they get fused to a larger 2-5 node. And what that results in is now this big node, this root node just has 15 and 20 in it. This left child has 2 and 5 fused together, and everything else is the exact same. Now, after you do fusion, you have to check you're not necessarily done. You look at the node that you pulled data from, in this case this 1520, and you make sure it's not underflowed. In this case, very clearly there's still data in this node, so I didn't cause more underflow. So I'm done. And again, for diagramming questions, check 2 data, 3 children, the order property fits for everything. It's a good indication that you did the question right. But fusion operation, pull from that parent, fuse with an immediate sibling, check for underflow in the node you pulled from. If you think about it, this is mostly going to be me stalling to give you more time to write things down. If you think about it, how 2-4 tree nodes operate is honestly quite similar to small children. They run out of things, they go see that their big sister, big brother, little brother, whatever, that little sibling, big sibling has things that they want, and they go and complain to their parents. They say, hey, my older brother's got extra data and I don't have any, gimme, gimme. And they complain and complain until their parents sort everything out. They redistribute everything so that the child is satisfied. In the fusion case, that's the child complaining to the parents because they don't have anything and they don't have some scapegoat like an older brother or something to blame it on. So they're just complaining to their parents until the parents finally inevitably give in and force children to share instead of just redistributing things like they did in transfer. Maybe that analogy is useful to some of you. Maybe it's not. Hopefully you at least have had time to write things down. We're about to move on to a much more complicated example that I've given its own page to. That's going to be an example of fusion and transfer. Give a couple more seconds, then we'll move on to that. I guess I might as well do this. In an alternate reality in which we chose to fuse with the right sibling, what would have happened is we would have had 5 and 20 in our root, The 2 node wouldn't have been touched, but instead we would have pulled 15 down and fused it with the 17 node. And then over here would be the same. So this is our alternate reality. So it gets a squiggly arrow. This is what would have happened if we had fused with the right child. Here we didn't have an option which to do transfer from, but normally you would get to pick, or it would be defined for you in the problem which you should choose. Here we technically had a choice. You can imagine that if fusion happened in or if underflow happened in the 2 node, we obviously wouldn't have a choice because there's only one sibling to fuse with. Alright, let's go on to our complicated example. I see someone asking what would happen if we removed 15. I assume you mean from here. Remember that when we remove an internal node, we use predecessor or successor to make it a leaf removal. So in that case, what happens depends on whether you pick predecessor or successor. If you pick predecessor, there's no underflow. If you pick successor, you'll have to do a transfer operation. So let's do a complicated example. This has basically everything that a remove could possibly include, all wrapped up into one awful bundle. So we are going to remove 25. Now, I find 25 in my tree, it's right here, and I want to remove it. But remember that 25 is not a leaf node. Remember, I'm only allowed to remove leaf nodes. So what I'm going to do is I'm going to replace it with the predecessor or the successor. In this case, it won't matter, but I'm going to choose the predecessor. For reference, the predecessor would be 21, the successor would be 35. For larger trees, just look at all of the data in the tree and find the data that in order would come immediately before it and the data that would come immediately after it. Those are your predecessors or successors. You can still follow that general rule of go left once, then go all the way right, or go right once, then go all the way left. It's just a little less obvious with 2-4 trees what that entails. So remember when I remove with the predecessor, I replace it with what was in the predecessor, and then I remove that node instead. So now I have a 21 in the node where 25 used to be, and the node where 21 used to be, that's the node I removed from, so that node became blank. Now, step 1, check for transfer. Now, it may seem like I have 2 nodes to check against here, 2 siblings, but in actuality, I only have 1. 13 is not a sibling of 21, it is a cousin. Transfer does not look at cousins, it only looks at immediate siblings. It only looks at 35, says 35 has 1 piece of data, I can't do transfer. And in this case, since I'm not allowed to do transfer, my only option is to do fusion. If we remember how fusion works, we pull down 21, the data in the parent, and then we fuse it with the sibling. Here we obviously only have one choice of what to fuse with. Nothing here on the left changes yet. Then what happened here is this node no longer has data in it because we pulled 21 down. Versus this child node now has 21 and 35 fused together. And this looks weird. We have a node with 0 data and 1 child in it. Remember, that still follows our property that we have 0 data and 0 plus 1 children. So I mentioned that that was still okay. But obviously for our 2-4 tree, this isn't okay. We need to have something in this node. So how do we fix it? We've caused more underflow. Step 1, check for transfer. I look at my immediate sibling node. I see, okay, it has more than 1 data. I'm allowed to do transfer. We go ahead with transfer. But remember, these transfers are rotations. I'm going to be moving the data around. This 15 is going to come down, and this 12 is going to come up. But notice this child over here. 12 has a right child. when we do our transfer and 12 moves, that child needs to move with it. You'll see if you forget to move this 13, you're going to end up with an invalid 2-4 tree. So, what happens next? I'll move this way. Is 12 is going to come up to the root. So we're left with just 5 over here. 15 is going to come down to this node. 1 and 10 didn't move. But this 13 child, that one is going to have moved all the way over to this side. And again, if you see, this is the only spot where this 13 child fits. If you tried to put it anywhere else in the 2-4 tree, it wouldn't satisfy the order property. Remember, it needs to be greater than 12, so it needs to be on this side of the tree, and it needs to be less than 15, so it needs to be over here. Then finally, this fused child, this 2135, that's going to be over here. Because we did transfer, there's no reason to check if we have more underflow. We know that our operation is done. So we can check, for a diagramming perspective, we can check, make sure everything in our 2-4 tree is good. 1 data, 2 children, 1 data, 2 children, 1 data, 2 children. Order property fits, 1's less than 5 is less than 10. 5's less than 12 is less than 15, and then 13's less than 15 is less than 21 and 35. So all the order property fits, all the shape property fits, all these leaves are on one level, so we're done with our operation. And these are really complicated examples, but just following that basic process, check for transfer, do it, or do fusion. That's it. There's never any other, when it comes down to it, that's all you have to do. I'll give a couple more seconds for people to write this down, and then we will be done with 2-4 trees, and we'll be moving on to an introduction to sorting, which we're not going to get that far. We're pretty much going to cover like what some of the terms mean and do 2 of the most basic sorts, and then we'll have a lot of time left for review at the end. All right, let's go ahead and take a look at sorting. So first, although it should be pretty intuitive, I'm going to say, what is this sorting that we're trying to do? This is some problem, so what's the problem we're trying to solve? So given some items, so elements in an array usually, and some way of ordering them, which I'll talk about later, we are going to sort the items, so we're going to rearrange them so that they are in ascending order, usually. For this class, we're going to do ascending order. Sometimes you might have to sort things in descending order, but we're going to do ascending order in this class. That's smallest to largest for those that get them confused. Now, I say some way to order them here. What do I mean by that? Well, remember from your BST, Heap, and AVL homework that one way to order them is if the objects implement comparable, we have some way of inherently comparing every object to the other objects in our array, usually. We call that the natural ordering if objects implement comparable. That's kind of the natural way those objects order themselves. But another way of ordering them, and you'll see this on your homework PDF because it's how we do it on the homework, is an object called a comparator. So comparators are kind of like machines that you give them 2 elements and it tells you what order they're supposed to be in. This comparators allow you to sort things that are not comparable, and it allows you to sort things that are comparable in a different order other than the natural ordering. So comparators are really useful, and once your homework gets released on Friday, check out the homework PDF and see the details on how to use them. Otherwise, you're free to look at the Java API for comparator to see what that looks like. The reason we do it with a comparator on the homework is it lets us count the number of comparisons you do, and that helps us track efficiency a little bit better. That also makes it a little easier for you to make your own code efficient, because you have direct feedback from JUnit tests. Also, most of these sorting methods aren't going to have return values. You're just going to get an array passed into the sorting method, and you're going to modify that array directly instead of returning a sorted array. Now, a couple properties we're going to talk about with sorts. Obviously, I didn't list it here, but obviously we're going to talk about efficiency, so best, average, and worst case. Since we're in the algorithms portion of the class, I've mentioned this a couple times already, but once we've at algorithms, best case is going to get a lot more meaning, and what a best case is actually going to have some sort of significance. So you'll see that later when we talk about our first sorts today. But a other property we can talk about is in place or out of place. So some of these sorts, not the ones we're talking about today, but some of these sorts are going to need to create other arrays or other data structures, so like array lists or something else, in order to work. They can't work without making this extra space from all of these extra data structures. Note that's data structures, not just like variables. If we need to create these extra data structures, our sort is out of place. You might imagine that using these extra data structures means that we're probably going to be able to make faster sorts by using extra memory. If you've heard us mention like space efficiency before, this is where space efficiency is really going to come in. Another definition is an in-place algorithm has a space efficiency of O of 1, versus an out-of-place algorithm has space efficiency that is not O of 1. We're not going to see any out-of-place algorithms today, but when we talk about some next week, you'll see examples of what I'm talking about. Stability is the next one. So stable sorts maintain the relative order of duplicates. Now what that means is if I have multiple of the same item, and when I say same, I mean same relative to this comparable or this comparator, if I have those in my starting array, after I'm done sorting, those should be in the same position relative to each other as when I started. A good example of how stability is useful is if I'm trying to sort by more than one thing. So say I have a group of names, like the group of students taking 1332, and I sort them alphabetically by first name. Then I sort them by major. So when I sort by major, you can imagine a lot of students have the same major. So those are going to be considered duplicates in my sort. But what's going to happen to all of those students that have the same major? Maybe I have like all the CS majors get sorted first, then all the engineering majors get sorted after that, etc. What I want is all of those CS majors to be sorted by first name. And if my sort is stable, that's going to happen, because those duplicates used to be in order by first name, so after sorting, they're still in order by first name within themselves. Once we talk about a sort called Lsd Radix Sort, you'll see a sort that uses stability a lot, but there will be a lot more sorts that actually maintain stability, and you can imagine that losing stability might be a trade-off for faster speed, just like having out-of-place sorts might be a trade-off for faster speed. And the last quality we talk about is adaptability. So an adaptable sort is some sort that makes optimizations if the items are already sorted or if they're nearly sorted before we start. A general rule of thumb you can use for this is that you can compare the best and average efficiencies of a sort. If you notice that you've got a best case that's better than your average case, usually that means your sort is adaptable. In this class, I think it's always true, but it's not necessarily true in general. But basically this means that if you're given really good input, you can terminate your algorithm really fast. I'll give people a couple more seconds to write this down, and then we will go ahead and start talking about Insertion Sort, which is the first sort of today. Only going to do 2 sorts today as a look ahead. We're going to do Insertion Sort, and then we're going to do Bubble Sort. Alright, let's get on to Insertion Sort. So how Insertion Sort works is we are going to divide our array into a sorted section on the left and an unsorted section on the right. Then our algorithm is going to repeatedly, I can't spell unfortunately, but we're going to repeatedly insert these elements. We're going to take them from the unsorted part and insert them into the sorted part in their correct position. That's the big idea of this algorithm. How it works is we assume that the first j elements of our array are sorted. And you can see that if we start j at 1, then we can use this assumption even at the start of the array, because one element is always sorted in itself. That's a very useful rule we'll use a couple times with sorting algorithms. But one element is always a sorted element within itself. Then what we're going to do is we're going to bubble the j plus 1th element, so the element right outside our sorted section. We're going to bubble that element backwards to its sorted location. And what I mean by bubble is we compare it to the element right before it. If they're out of order, we swap, and then we keep doing that. We keep making swaps backwards until we find its sorted location. Then we're going to repeat this entire process until the array is sorted. So that's when j is the entire array. Then the first entire array elements are sorted and we're very clearly done. A useful kind of invariant that insertion sort holds is after iteration I, the first I elements in our array are always sorted, but note that they are not necessarily in their final positions. So it's possible that the very first element in our array is the largest element. So that element will be sorted relative to itself, but it obviously is not in the final position relative to the whole array. And you'll see an example of that when we actually walk through an example of insertion sort in about 5 seconds. So I could redraw out an array like 10 times and rewrite data a million times to show you guys, but a more fun way to do sorts is with something dynamic like cards. Wow, crazy. Jacob using cards for an example for something? Never heard of it. So I've got some cards here. I'll try to go slowly enough that you guys can write out these examples if you want to try and follow along. But I've written out the starting array there if you want to get a little bit of a head start. Try to spread these cards out as much as I can, but unfortunately they would go a little bit beyond my screen length if I put them all out. So these are the things I'm going to be sorting. This is my array, and I'm going to perform insertion sort on it. So the first step of insertion sort is essentially splitting up the array into the sorted section and the unsorted section. So I'm going to do that by kind of having this gap in it. We start with this one element, 6, in its sorted position. So this array is sorted, this array is who knows. Then we're going to start taking elements from the left side of our unsorted section, and we're going to insert them into the right side. So how we do that is we take this element over, and we compare it to the end of the sorted section. We say, are these two out of order? Is this element less than this element? In this case, the answer is no, so I don't need to do a swap. If insertion sort ever does not need to do a swap, we immediately stop and move on to the next element. So now this array is sorted, and I grab my next element. I compare it to the edge of my sorted array. These are out of order, so I'm going to swap 9 and 3, and I keep going. I take 3 again, and I compare it to the next thing. 3 is less than 6, so 3 and 6 are going to be swapped. Now we've reached the beginning of the array, so I'm clearly done, and this is my new sorted portion. Now we can do the same with 2. 2 is less than 9, so they swap. 2 is less than 6, so they swap. Try to not cover things up too much. And 2 is less than 3, so they swap. I've reached the beginning of my array, so 2 is in its correct sorted position. And these are what everything looks like right now after that iteration. Next I grab this 4. 4 is less than 9, so these swap. 4 is less than 6, so these swap. Sorry. Then 4 is not less than 3. So now I both don't swap and I stop doing comparisons. So 4 never gets compared to 2. After this, 4 compares to 3 and determines that a swap is not necessary. We don't need to do anything. We just stop immediately. And you'll see, especially with this next element, that can save us a lot of time. So 8 is less than 9, so those are going to swap. Then 8 is not less than 6, so these don't swap and we stop. We don't do any comparisons with any of these elements. So this is what we've got right now. You can see again, this is a sorted array. It just doesn't have all of the elements in it. So we take 7. 7 is less than 9, so it swaps. 7 is less than 8, so it swaps. 7 is not less than 6, so it's found its correct position. 5 is less than 9. 5 is less than 8, so they swap. 5 is less than 7, so they swap. 5 is less than 6, so they swap. 5 is not less than 4, so they do not swap, and we found our correct position. And since we've added every element to our sorted array, we can see that our entire array is now nice and sorted. A nice way to think about insertion sort is it's thinking about like if that sorted portion of the array was like your hand of cards in a card game, and all of the cards from the unsorted array were cards you were drawing and adding to your hand. Think of it like taking that card and adding it to the correct position in your hand to keep your hand as a sorted hand, essentially. That's another way I'd like to think about insertion sort. Regardless, the next thing we're going to talk about with insertion sort is its properties, the ones I mentioned on the previous page. The best case for insertion sort is an already sorted array. If we have an already sorted array, then all of those bubblings down stop immediately, and we basically just traverse over the array once and are done. The worst case of our insertion sort is a reverse sorted array, so an array going in backwards order, so highest to lowest. In that case, we have to bubble the first element down once, the second element down twice, the third element down 3 times, all the way through the end of the array. So you end up like 1 plus 2 plus 3 plus all the way up, all the way to plus to n. And that is O of n squared. Because if you remember, that's like n squared over 2-ish. But we drop those constants for big O. So this is how we get that our best case is O of n. Our worst case is O of n squared. For insertion sort, it turns out our average case is also O of n squared. There's not much of a proof for that one I can really give you, but you can imagine that on average we still have to do a lot of swaps for this sort because it's constantly comparing things next to each other. As I mentioned, we didn't need to create any other arrays or anything else for insertion sort, so it's in place. Determining if a sort is stable can be a bit tricky without like counterexamples, but in this case I'll tell you it is stable. If your sort is based off of only comparing like adjacent elements to each other, that's an indication that it's probably going to be a stable sort. And then our sort is adaptable. If we started with a sorted array, we would have pretty much been done instantly. If like one element was out of order, then like that's the only element that would have needed to be bubbled down. Everything else would have worked out very quickly. So it is adaptable. We do get improvements off of starting with an array that's nearly sorted. Give a couple more seconds for people to write that down, then we'll talk about bubble sort. Alright. Last page of new material. Bubble sort. So, how bubble sort is going to work is we are going to repeatedly swap adjacent out-of-order elements in a way that's going to move or bubble the largest element up to its proper location every single iteration. It's kind of like the one-liner description. How it works, each iteration, we start with the first 2 elements in the array and we compare them. If they're out of order, we swap them. Regardless of whether they're in order or out of order, then we move on to the next 2 elements. And we're just going to repeat this process until we get to the end of the array. Now this process overall is relatively slow because we need to go all the way to the end of the array. We're going to need to do it n times in order to check everything. But we can make it a little better. We note that after the ith iteration, the last I elements are in their correct place, so there's no need to compare anything to them. And remember, that's because our first iteration bubbles the largest element all the way up to the end. So the second iteration bubbles the second largest element all the way up to the end. So on our ith iteration, we don't need to compare against the last I elements in the array. But it turns out we can actually do a little better than that. We can remember the location of the last swap we performed in bubble sort. So if we swap a bunch and then stop swapping, like here randomly, before we go on to the rest of the array, then future iterations can stop here where the last swap happened. Nothing else is going to need to be swapped beyond that. So we can make even better improvements by recording where this last swap happened. This also lets us make another cool optimization, that if no swaps happened, if we do one entire loop of the array with no swaps, we automatically terminate. Which makes sense, because if no elements are out of order with the things next to it, that means our array is sorted. So I've talked about this enough. Let's see what it might look like in action. I've given you my starting array here, but I'm going to be using cards again. And here I don't really have a sorted section, but I will have that like largest section, and I'm going to move that to the side so you can see what part we don't need to compare against every time. So, bubble sort. Start at the beginning of the array, compare adjacent elements. So I compare 3 and 2. They're out of order, so I swap them. I'll use this pen to kind of keep track of where I am. Now I compare 3 and 8. Those are in order, so I keep going. 8 and 5. Those are out of order, so I swap them. 8 and 9 are in order. 9 and 4 are out of order, so I swap them. 9 and 6 are out of order, so I swap them. Then 9 and 7 are out of order, so I swap them. And in this case, my last swap happened at the end of the array, so only the last element gets moved over. I can't get any more information than that. Then I start again. 2 and 3 are in order, there's nothing to do. 3 and 5 are in order. 5 and 8 are in order. 8 and 4 are out of order, so I swap them. 8 and 6 are out of order. 8 and 7 are out of order. And then that was the last swap of my array. So again, the 8 is the only thing that gets to move over, because I swapped at the very end of my array. But this time we're going to make some improvement. 2 and 3 are in order. 3 and 5 are in order. 5 and 4 are out of order. 5 and 6 are in order. 6 and 7 are in order. Now in this case, the last swap I did was the swap of this 4 and 5. So that means all 3 of these elements, the element I swapped upwards and the everything that comes after it, get moved over. I don't need to compare them again, and you can very clearly see that they're in their correct positions. Now I'll do one last iteration, because we don't know for certain that this part is sorted yet. 2 and 3 are in order, 3 and 4 are in order, and because I did no swaps, we're guaranteed that our array is in its correct sorted order. And that is bubble sort. It's just comparing these adjacent elements. Most people have done this in some previous class at some point. It's a very simple sort to implement at its core. That optimization can get a little tricky, but overall it's not that bad. And I didn't rewrite them all down here, but the efficiencies and properties are completely identical to insertion sort. So that might save you some writing time, or you can just copy it. But the efficiencies are the same, the in-place stable adaptable are the same. It's still the best case for a sorted array and the worst case for a reverse sorted array. So that's all I've got for sorting. Now we're going to move on to review stuff. So I'll leave this on screen for a couple seconds more for people to write that down, but I will also pull out, if you remember, we had that Kahoot last time that was at the tinyurl exam 1 review. Now if you go to tinyurl.com/1332 exam 2 review, which I can write down also. Put that in the Q&A so you guys can see it. That will have some review questions in a Kahoot that you guys can use. Obviously, we can't really do that virtually over Recitation, but feel free if you want to get in groups with yourselves and try to play that, or just look at the questions and answers. Feel free. Now I will start to look through some of the questions you guys asked earlier, and you guys can ask some more questions that are review-based. TAs can try to help answer those, but I will also be going through myself and answering what I can. Here we say, can we go over big O for heaps, hash maps, AVLs, and 2-4 trees? So I already talked about 2-4 tree operations, but I can talk about some of the other ones. So heaps, if we do like add, remove, these are the important ones. In general, remember that remove is going to be O of log n for worst case. These are worst case, because those are the important ones for heap. Because average case is a little funky, and best case is kind of trivial. So remove is going to be a log n operation. Add is always also going to be log n, but remember that it is amortized, because we might have to resize the array. We've also got build heap. That's O of n. Hash maps are there too. So hash maps, say add, I'm going to put these, but they're the same for, like, get and contains are the same, etc. too. So we've got average and we've got worst. On average, add and remove are going to be O of 1. In the worst case, remove might be O of n. Versus add, in the worst case, if we look at that, that's going to be O of n amortized for probing, or just O of n for chaining, or O of n squared unamortized for probing. And that's because probing with a lot of collisions can be n squared in the resize case, but chaining can never be n squared. So in the worst case with a bad hash, chaining is O of n, versus in the worst case with a bad hash, probing is O of n, unless we have to resize where it can potentially be n squared. AVLs are basically log n for everything. Someone said, how can we access questions from the Kahoot? Hopefully that link works. If that doesn't, I will have to ask Neha about that, because I believe she made that. Another TA might be able to help me out and ask her about it. Heapify, so what it is. So heapify could refer to up or down, but both of them are log n in the worst case. Here, since heapify kind of inherently doesn't include the adding or resizing part, there's no amortization necessary. We do not search for things in a heap, because that's not what heaps are for. If you wanted to, it would be really ugly, and you'd have to do a bunch of removals and adds to make that work. But we might have like a get, min, or max operation. That's O of 1 time. So what resolution strategy you choose for your hash map? Someone asked a question about it. What resolution strategy you choose is kind of problem domain dependent. External chaining is really popular because you don't have to do all this complicated probing math. You don't have to worry about some of those infinite loops we mentioned last time. Last time we talked about hash maps. You'll note that Java's implementation uses a variant of external chaining, but quadratic probing and double hashing both can give us better data spread out compared to linear probing, but quadratic probing and double hashing both have issues with infinite loops, and double hashing relies on your ability to choose a good secondary hash function. So they're not flawless methods. What are efficiencies for priority queues? Priority queues are exactly the same as heaps. Remember, they're just heaps wearing trench coats, so their efficiencies are the exact same. Except Stuff like heapify doesn't have meaning in a priority queue because it's not an operation you do. Can we have a real-world example of when you'd want to use an AVL heap hash map 2-4 tree? So heaps, anytime you're looking at data structures where all you really care about is keeping track of what is the smallest thing in it or what is the largest thing in it. It's kind of hard for me to give like specific examples without like saying test questions that we've used. AVLs are just useful for when you're storing lots of data and you want to be able to search for things in good time, and you've got enough memory to spare that an AVL is fine over something like a BST. Hash maps are incredibly useful anytime that you've got data that you can want to be able to like check up some access pairing, so you want to have like a key you look up and a value you get back, so think like a dictionary, think like a contact list, anything like that, where you want really fast access speeds. That's when you're going to use hash map. 2-4 trees are other alternative implementations you could use instead of AVLs. Your operations get a bit more complicated and your efficiency gets a little sketchier, or not your efficiency, your edge cases get sketchier, but a nice thing with a 2-4 tree is that I mentioned all of its efficiencies were log n, but with 2-4 trees that actually ends up closer to log base 4 of n instead of log base 2 of n, which practically is a little bit less even if it's the same big O. So someone wanted some AVL rotation examples. Someone mentioned heap sort earlier. I'll link a good video about heap sort. And I promise I'm not just saying that because I made it. Definitely not just egotism. Let's do a AVL rotation. You're going to have to give me a second to come up with a good example. Let's see. I want... This should work. All right, let's get my heights and balance factors written down. So, we see here that we have a unbalanced AVL. We've got this thing that is left heavy, and this node that is, this node is critically right heavy, and this node is slightly left heavy. So what's going to happen first is we need to do a double rotation. That's going to be a right rotation on 30 and a left rotation on 20. The first right rotation is going to involve pulling 25 up and 30 down. So you'll see 25 goes up, 30 goes down. That's that right rotation. But someone asked about these children moving along. When 25 gets pulled up, this 27 needs to move over. And you get something like this. This is an example of not checking for rotations in the middle of your double rotations. Because if you did, you would see that this node would try to rotate again in the middle of your double rotation, and that would end very poorly. So then we do our right rotation about 20, and that's going to get you 25 at the top, 20 comes down, then 30, 27, 40, 10, and you're free to recalculate those balance factors on your own. But that's an example of a rotation where the children are moving around a bit. Amortize. So someone asked, wait, so amortize can also apply to having a bad hash function, not just resize. So in here, the worst case says that we have a bad hash function. The amortized tells us whether or not we're resizing. That's one way to think about it. How can you look at a tree and notice if it's a BST or AVL without calculating the balance factor and height? Yeah, if a tree is balanced, you don't know whether it's a balanced BST or an AVL. If the tree is unbalanced, it's clearly a BST. On a diagramming question, we would say whether you should be working with a BST operations or an AVL operations. Splay trees are no longer taught in this course just because of how time and stuff moved around. Heap add is worst case O of n if you are looking at unamortized analysis. Let's see. When doing rotations, you do them as you go up the AVL. Yes, that is correct. What is the difference between scenario of AVL and a BST? If you've got memory issues, so you know that you don't have like as much memory to use, a BST might be better, because remember, these AVL nodes all have to store a ton of extra data in them. And also, BST operations on a balanced BST are a little faster than AVL operations because we don't have to do these rotations at all. Even though they take constant time, that's still actual time they're taking up. And remember that BSTs on average are still log n, so those degenerate cases don't usually happen that much. So we can usually get away with using a BST, but sometimes we want to make sure that things are balanced, and we're fine with that extra memory and small extra time cost in exchange for ignoring that degenerate case. We got a question, if skip lists going to be on the test? Yes, they are on the topic list. They might be on the test. If so, can we go over them real quick? I don't know exactly what you want me to go over, but I can look at them quickly. I recommend rewatching parts from last week's recitation. I think last week? Whatever week I did skip lists on. But remember, how we do them is when we do adds, with skip lists, what we do is we look for the correct spot to add. So let's say I'm trying to add like 60 with the coin flips, heads, tails. I start here. 30 is less than what I'm trying to add, so I go. Here, I don't have anything, so I go down. I don't have anything to the right, so I go down. 40 is less than it, so I go over. 50 is less than it, so I go over. There's nothing to the right of it, and I'm on the bottom level, so I know I can add 60. I have one head, so I promote once. And that's my operation. Will you be asked to write the code on algorithms in exam 1? No, there will be no sorting code on exam 1, or wait, exam 2 I assume you meant. As per the topic list announcement, sorting is not going to be on it. You haven't even gotten your homework yet. What is the difference between complete versus full BST? So full BST is every node 0 or 2 children. Complete BST, every level has all possible nodes. Last level is filled left to right. So like these are full BSTs. These are complete BSTs. This one is full and complete for reference, but this one is just full and these two are just complete. Does external chaining method ever result in a resize of the array? Yes, and we still base that on the load factor, just like we did with probing. Are we also limited to 2 sheets for scratch work for this exam? Yes. When searching in a skip list, do you have to traverse down to the bottom level after you found the node containing the data on a higher level? No, you can stop as soon as you find it on the highest level, because it should be an exact copy of the data on every single level. Difference between a BST and a binary tree. BST has the order property that all data to the left of a node is less than it and all data to the right of a node is greater than it. Binary tree makes no guarantees about the relative order of anything. You're welcome, anonymous student. You're welcome, anonymous student number 2. Will hash map coding still be tested if you just got the homework back today? I mean, I'm not going to tell you whether it's going to be on the test or not, because I'm not going to tell you what's on the test. But it is still on the topic list, and it would still be fair game. because you have like all of today to look over that feedback we gave you, and you have like tomorrow before you take the exam, although we can't comment on office hours anymore. Just a reminder, remember that there's no office hours Wednesday, there's no Piazza Wednesday, there's no office hours Thursday, but there is Piazza on Thursday, although students would... Sorry, words. Although TAs will generally not be answering Piazza as much on Thursday because we're going to be grading your exam all day. Why is the runtime of getting the 5 smallest elements from a min heap O of log n? So on the surface, that seems like an identical question to that, like, get the third element in a linked list. But remember that we have to essentially call remove 5 times, and each of those remove operations takes log n time. Removing 5 things from a heap of size 10 is not the same as removing 5 things from a skip list of size 10 million. Because each of those removes has to potentially heapify an entire branch of the tree. So that's why that's a log n question. Is there a difference between hash map and hash table? Yes, but that doesn't matter in this course. Essentially, you can ignore hash tables and only think about hash maps. Hash tables have some things with synchronicity and like thread synchronization. How many coding questions will be on the test? That's not something I can answer, but the points from coding questions will be no more than 35% of the total exam. In general, it's very common that we ask 2 coding questions. We have asked 3 in the past, though, on other exams. We kind of accidentally had 3 on exam 1 for one of the sections. But that actually ended up not mattering very much, fortunately. They're not seeing any other major things. What is the worst algorithm for adding of heap without amortizing? I have to interpret that question. So if you're saying what is the worst case efficiency of adding to a heap unamortized, that is O of n, because that is the case where you have to resize. Is coding AVLs fair game for the exam? No, your homework's not even due yet. That's on the topic list. How many questions in total? The same, like, 8. 1 second. Make sure I can actually see. 8 questions. Remember that things like scenarios, even though there's multiple questions, scenarios counts as 1 question on the exam by our standards. It's basically, if we were giving it on paper, how many, like, what would be on 1 page? That's 1 question, basically, with a couple exceptions for things that take up more than that. Do you recommend redoing the reality checks to help studying? Oh, that's a good resource. A lot of people find that helpful. I'll go a little bit longer, but I am dragging TA's time out a little bit longer than I want to, because remember, this is their time slot that they set aside. And also, there's the restream. It's going to be happening later, where you can ask some more questions if you still need them. Ivan and Tashit may be able to help you out with that. Although people there will be covering the new content too. So if you're going to attend the restream also, please don't bombard them with questions, because some people will be there just to learn like the 2-4 tree content and sorting content. So be respectful of those people. Speaking of that, how many people did we get today? Pretty good haul, about 144. Someone asked, what is the difference between BST and binary tree? I answered that one already. BST has that order property that matters. Do we resize if you encounter size non-removed elements when probing? Assuming you're talking about linear probing, not necessarily. You only resize based on your load factor in linear probing. If you had 24 hours to study, what resources and what order would you recommend looking over for the exam? I'm a terrible person to ask about this. I have bad study habits because I have a good memory, so I don't usually need to cram. I can get by with cramming, which is a terrible advice for everyone else. But looking over your code, looking over some of the reality checks and some of the practice problems we do in Recitation, those are probably useful. Hopefully you might have some idea of like what areas you struggle in and what things you need to review. For topics already included in Exam 1, would you need to write code on them? It's unlikely that we would give a coding question that we already asked something about in Exam 1, but it's not impossible. But obviously we want to focus on the new stuff for coding, because that's the stuff that we haven't gotten a chance to ask about, and we might not get a good chance to ask about again. You're welcome, anonymous student number 3. Can I go over double hashing real quick? Real quick? Probably not. But remember, we have a second hash function. Let's call it like, we've got h of k, and we've got like equals h, and we've got like h2 of k equals d. And when we probe, we're going to check h, then h plus d, h plus 2 times d, h plus 3 times d, etc. That's double hashing in a nutshell in 30 seconds. Then I think once this catches up to reality, I'm going to cut it off. Didn't get a chance to do a card trick today, which is a nice cover for the fact that I only got to even practice it once, and I couldn't even find the tutorial to link it to you guys. So, sorry about that. I will give TAs a chance to answer some questions that are remaining, but otherwise I'm going to quiet myself and let it catch up so I can end the recitation for the sake of people that have things to do and for the sake of the restream. Thank you guys for coming. Good luck on the exam tomorrow.